Okay, hello everyone. First of all, it's my great pleasure to be here, and I would like to thank the organizers for hosting this wonderful workshop, and thank you for giving me this opportunity to share my research. So I'm Ting Wen Lan from National Taiwan University. In the following, I'm going to talk about unveiling the multiphase properties of the circumgalactic medium of star-forming galaxies at redshift 1.5. And this is an ongoing project in collaboration with Xavier Prochaska and the DESI collaboration. So as we have learned from this workshop that the multiphase properties of a circumgalactic medium can be extracted via absorption-less spectroscopy by detecting absorption-less trace gas with different phases. For example, neutral hydrogen and magnesium to absorption line can be used to trace gas with 10 to the 4 Kelvin gas, and carbon-4 trace gas with hotter temperature, about 10 to the 5 Kelvin, and oxygen-6 trace gas with hotter temperature, 10 to the 5.5. And the UV spectrograph has been widely used to detect as many absorption lines as possible once within the wavelength coverage of the instrument and simultaneously investigate the multiphase properties of CGN. And as we have learned a lot from this workshop that we can learn the multiphase properties of CGN at relatively low redshift, below redshift 0.5. And this redshift range is just limited by the wavelength coverage of the UV spectrograph. But the next step one can try to pursue is try to understand the cosmic evolution of the interaction between the multiphase circumgalactic medium and the galaxies. And in order to do so, we need to shift into the optical region, try to detect absorption lines that trace gas in different phases using the optical ground-based spectroscopy instrument. For example, magnesium to absorption line can be detected in the ground-based optical region from redshift about 0.4 to 2.5. And carbon-4 shift into the optical region about redshift 1.4. In other words, redshift 1.4 is the starting point for us to revisit, to explore the multiphase properties of circumgalactic medium if we try to understand the cosmic evolution of the interaction between the gas and the galaxies. But the challenge here is that, in fact, constructing a large sample, a large statistical sample of galaxy and quasar pairs at redshift 1.5 requires substantial observational resources. And the challenge is not detecting those absorption lines. The challenge is actually getting the redshift of galaxies. And this basically limits the previous studies to explore this cosmic epoch of study the galaxy and CGN connection at redshift 1.5. But now the situation has changed. Now we have large sky surveys, the dark energy spectroscopy instrument survey, which provides us tens of millions of spectroscopy measurements which obtain spectra of extragalactic sources across a wide range of redshifts. And using this large data set, now we can explore the circumgalactic medium, multiphase circumgalactic medium properties at least redshift 1.5. And if I'm interested, I'm happy to talk more about DESI and the data set, but just to give you a visual impression about the information that DESI provides, here is just a random footprint on the sky, and the background is a DESI legacy imaging surveys. And these are the sources with Sloan spectroscopy measurements, and these are the sources with DESI spectroscopy measurements. So you can see that DESI will provide many more spectroscopy measurements, which will be 10 times more than the previous Sloan digital sky survey can provide us. And in addition, it will cover a wide range of redshift up to redshift about 1.6. And currently, DESI just finished its third-year operation, which already includes many, many galaxies. So it provides us about 1.6 million emission-line galaxies, which are star-forming galaxies, produce strong emission lines at redshift just between 1.4 and 1.6. So it's just a narrow redshift region, but it's already 1.6 million emission-line galaxies. And together, there's a million quasars at an even higher redshift, and combine this sample together, we can construct a large statistical sample of galaxy and quasar pair at this redshift. So currently, we have about 7,000 galaxy and quasar pairs at this redshift within 300 kiloparsec. And we can utilize this data set to explore the galaxy and CGN connection at least 1.5 redshift at 1.5. Just to give you a sense about the data set, here in this image is a galaxy and quasar pair. The galaxy is actually quite faint, so it's very hard to see the galaxy in this image, but it's robustly detected. Here is the spectrum of the galaxy, the DESI spectrum of the galaxy, and in black, you can see that the galaxy spectrum is mostly consistent with 0, and most of the pixels are featureless. But there's actually one peak over here. That's O2 emission line. So if we zoom in, you can see the two transitions from the O2 emissions. And using these features, DESI can actually obtain the ratio of the galaxies. And we can also estimate the star formation rate based on, for example, the O2 luminosity. And let's move to the quasars. So here is the quasar spectrum. And you can see it's a typical broad emission line quasars. But you can see that there are absorption line features over here. That's magnesium-2 absorption lines. And there are absorption line features over here. That's carbon-4 absorption lines. So with this data set, we can simultaneously obtain magnesium-2 absorption line trace cool gas, 10 to 4 Kelvin gas, and carbon-4 absorption line trace gas with hotter temperature, about 10 to 5 Kelvin. And with this data set, in following, I'm going to just address one question. How do the properties of gas traced by magnesium-2 and carbon-4 correlate with the mass of the galaxies? Okay, and I'm going to just start from magnesium-2 absorption lines, the cool gas. In this plot, I'm showing the rest equivalent width of magnesium-2 absorption line as a function of impact parameter. And the black data points are measurement with more than 3 sigma detection, and the gray data points are just measurement with below 3 sigma detections. And you can see that in the inner region, the magnesium-2 absorption line on average is stronger compared to the outer region, and this is actually consistent with the measurement at low redshifts. And we can try to use a simple measurement, just calculating the average absorption line strength as a function of impact parameter to summarize this behavior, which are shown by the blue data points. Now the blue data points are just the average absorption as a function of impact parameter. And at larger scale, you see that the average absorption is actually below the majority of detected sources. It's just because there are a lot of measurements without 3 sigma detection below. So it's actually driving the measurement. And we can consider this average absorption as a combination of covering fraction of the gas distribution times the average strength of detected sources. And in the following, I'm going to just show you the average absorption and explore how this correlates with the mass of the galaxies. So we can start with galaxies with lower mass. Now I'm showing you the average absorption line strength as a function of impact parameter around galaxy with 10 to the 9.5 solar mass. And I'm going to increase the mass. Now it's 10 to the 10 and 10 to the 10.5. And you can clearly see that the average strength of magnesium-2 increases with the mass of galaxies, suggesting there's a correlation between the two. But now, the x-axis currently is a physical space, but we know that the galaxies live in different halos. So small galaxies live in small halos, massive galaxies live in large halos. So we can try to normalize the x-axis by the virial radius of dark matter halos and revisit this plot. So now I'm changing the x-axis. Now this is the impact parameter divided by the virial radius. Again, this is the average absorption around galaxy with 10 to the 9.5 solar mass, 10 to the 10, and 10 to the 10.5. And you can see clearly now, once we normalize the impact parameter by the virial radius, the measurement now align with each other, suggesting that somehow the gas within the dark matter halo, they behave similarly around galaxies and across different stellar mass of galaxies. And we can just characterize this behavior by an empirical relation, exponential profile plus a power law in the inner region. And this is, in fact, not the first time we see this behavior. So at relatively low redshift, about 0.5 to 1, we also see this behavior for magnesium-2 absorption lines. So now the next question we can ask is whether or not the carbon-4 absorption line has a similar behavior. So we can play the same game, do the same measurements for carbon-4. Now the y-axis is the rest equivalent width of carbon-4 as a function of impact parameter. And again, those are detected sources and non-detections. And we can calculate the average absorptions and look for correlation with stellar mass. So now this is the average absorption strength of carbon-4 as a function of impact parameter around galaxy with 10 to the 9.5, and 10 to the 10, and 10 to the 10.5. And again, you can clearly see that there's a correlation between the average strength of carbon-4 and the mass of the galaxies. Again, we can normalize the impact parameter by the virial radius. Now, again, 10 to the 9.5, 10 to the 10, and 10 to the 10.5 solar mass. And you see that the carbon fraction the average absorption of carbon-4 now again align with each other and they behave consistently within dark matter halos. So now we can come back with this question: how do the properties of magnesium-2 and carbon-4 correlate with the mass of galaxies? And the answer is, in physical space, they correlate with the mass of galaxies. Both the strength of magnesium-2 and carbon-4 increases with the mass of galaxies. But once we normalize the distribution by the size of halos, then the profile becomes similar across stellar mass. Before I end my talk, I just want to emphasize that although the gas traced by magnesium-2 and carbon-4 they have similar correlation with the properties of galaxies, they do behave differently around galaxies. So if we look at the average absorption for magnesium-2 in blue, and now I'm showing you again the average absorption for carbon-4 in red. And you can clearly see that the magnesium-2 somehow can be even stronger in the inner region. It decreases rapidly as a function of distance from galaxies, while the carbon-4 is sort of flat in the inner region and it gradually decreases at larger scales. And I believe that this might reflect the fact that the gas traced by magnesium-2 and carbon-4 they have different 3D distribution in the halos. And I believe with these new measurements at redshift 1.5, combining the measurement at low redshifts as well as the measurements at high redshift enabled by JWST, we will have a more complete picture about the cosmic evolution of multiphase CGN and galaxies, and possibly have a better understanding of the underlying mechanisms driving this observed phenomena. I will stop here. Thank you.
Time for questions. Interesting talk. I'm wondering if you could say something about how this, the strength of the absorption, etc., compares to the lower redshift observations we have already, and is there an evolution?
That's a good question. So, thank you for asking. Let's see. Where is it? So in fact, although in my talk I just showed the average absorption, but actually people also like to estimate covering fraction, which describe what's the area covered by the loss absorption lines, and we can compare the covering fraction redshift evolution. So from this is the covering fraction for magnesium-2 at redshift 1.5 from this work, and it's just including the absorption line strength higher than 0.4 angstrom. And this is my previous studies at low redshifts from redshift 0.6, 0.9, and 1.2. So it's, I would say that it's actually similar or consistent with the combining previous studies. Actually, there's a redshift evolutions, and it's consistent with continue to increase the covering fraction for the core gas traced by magnesium.
Yeah, very nice talk. I had a question about where the carbon-4 comes from. So locally, a popular model for carbon-4 is like interfaces or mixing layers between cool clouds and a hot CGM. Could that be working here? Could we be seeing interfaces?
That's a very good question. So actually, I have been trying to understand what caused this. So maybe I cannot provide you an answer, but I think what's interesting from the data is that, for example, here's just one system I showed, that within the small impact parameter, you can have strong magnesium to absorption lines and carbon-4. By a similar impact parameter, this is another system, you can have a similar carbon-4, but different magnesium to absorption lines. So if we just consider the carbon-4 is mixing layer of cold gas clouds, I would expect that they somehow correlate with each other better than what we observe. So I suppose there's much other mechanisms in play based on the data. Yeah.
Okay, let's the next speaker again.